formatted by Alex Glaser at Princeton, and I've actually cribbed some of his slides there, but all his information came from this document, so we're all good. In the first context I want to talk about is that you've heard about the single-stage weapons, fission weapons, the Trinity type, either gun type or the Trinity/Nagasaki type, which were characteristically tens of kilotons. You've also heard about two-stage weapons being basically fission-fusion weapons. In fact, they're fission-fusion-fission weapons, which get up into the megatons. In fact, the largest weapon ever exploded in the atmosphere by the Soviets in 1962, I think it was, called the Tsar Bomba, was 58 megatons or something. There are actually three, can we hit the lights here somewhere, kilolights? Three film, well, there are many, many, many high-speed photographs, still photographs, all kinds of other instrumentation at Trinity. There are just three that were taken 9,000 meters away, so that's about 5 miles. And each of these is some 10 or 20 seconds or something, with kind of different zoom. There's actually one intact color photograph, still photograph taken. There were other photographs that were taken with very fancy techniques that captured the light, the radiation in like 1 or 10 billionths of a second, because the thing evolves so rapidly. This one is the key one I wanted you to look at. So maybe I'll just pass on from there. And I now want to show that in contrast to the Castle Bravo test, largest bomb we ever exploded in the South Pacific. It actually was a bit of a mistake. It ran away. It was designed for about 8 megatons. It ran up, or 6 megatons, ran up to 15, actually endangered the scientists even a great distance away. You'll see several different angles of this. I want you to understand the qualitative difference. This is something, even a conventional megaton blast. That photograph, by the way, was taken, that footage was taken at a distance of 75 miles. When the Soviets did the upper atmospheric blast of the Tsar Bomba, it actually broke windows in the Scandinavian countries 1,000 miles away. It scared the Russian generals who were more than 100 miles away, because the heat in their face was like in an oven. They were actually really scared at what this thing was all about. Okay, now you go from the direct radiation, now you see the shock wave coming at a very, very, very great distance, and it basically destroys everything. Even reinforced concrete buildings are just many, many, many miles away, are absolutely leveled. Okay, let's quit this.
Is that footage real time?
Yes, that's real time. Okay, general categorization. There's thermal radiation, blast and shock, and then there's what's normally looped into one, which is the nuclear radiation. There's about 5% direct from the actual event itself, and then there's residual nuclear radiation, fallout, and from either the casing and weapons parts, and from the ground if any of that gets swept up. Let's pass over this. 2 or 3 important things. There's what's called an airburst, surface burst. The test at Trinity was a surface burst because it was put on a tower 100 feet high. An airburst, the 2 that were actually deployed in Anger, were detonated at 1,600 and 1,900 feet or so. And as Mr. Sokolsky was mentioning, these things can be used very effectively as anti-ship and anti-submarine mines because of the shock wave they set up in the water, which is a very stiff substance. can easily snap the hull of a ship even at a great distance. So they're very effective as anti-submarine devices. I'll talk about the difference between the definition between an air burst and a surface burst. It's very important just shortly. Thermal radiation, including light, 35%. The blast, 50%. Nuclear radiation, prompt and delayed, about 15%. First effect is the fireball. You've created this immense amount of energy in something which is only some tens of centimeters across. It radiates, for those of you who are physicists / engineers, as what's called a black body radiator. Given the temperature, the characteristic radiation coming out is a thermal spectrum of average temperature in the region of the X-ray. So keV, not half an electron volt associated with visible light, but many kilo electron volts, tens of kilo electron volts even. This immediately ionizes the air within a certain radius, and that's where most of the energy initially starts. In the case of Trinity, it was 1/4 of a mile apart. In the case of a megaton bomb, the fireball, you can see the 100-meter scale down there. That's not quite, I think at about 0.09 seconds, it was at maximum. In the case of the megaton device, that fireball is more than a mile. Okay, everything, all the air in that is ionized completely. Not fully stripped, but everything is completely ionized. You see in the case of the Castle Bravo shot, all these things, you immediately see, because you've created this very low density region, it's like a bubble in a glass of beer. All of a sudden, it's buoyant, and it is going up, in the case of a thermonuclear weapon, at hundreds of miles an hour. Immediately like that, this thing begins to rise. And in the case of a thermonuclear weapon, that cloud would go up to many tens of miles. So it would even go up to more than 100,000 feet. So it's a really prodigious thing. You also see a blast wave, and then you see this enormous suction wave coming back. So all of a sudden you see this hurricane force winds pulling everything into the base of the blast and then up. Difference between a surface burst and an air burst. A surface burst is where the fireball actually touches the ground. It sweeps up the dirt, may even make a crater, brings it up into the middle of where the explosion happened, and then now you get soil, earth, basically irradiated with an enormous fluence of neutrons, and now you get radioactive fallout. Surface bursts do not produce fallout because the fireball did not touch the earth and sweep up the dirt there. Whoops, okay. You now have a pressure wave. After 10 seconds, this shock front is out many, many miles. And let me just show you here, and then afterwards you will get you talk about the prompt radiation and the delayed radiation. Interestingly, when you design a weapon, depending on whether what you are targeting, generally you are making this thing go off at an altitude, if you want to destroy an industrial area or whatever, at an altitude to maximize the radius where you get an overpressure of about 15 psi. Normal air pressure is 14.7 psi. Interestingly, you say, well, if I were in a place with an overpressure of additional 1 atmosphere per square inch, you might say, is that a big deal? You can see the fatalities there, and even reinforced concrete structures at approximately that pressure are destroyed, reinforced concrete structures. If you're hitting missile silos and so forth, which are hardened, you have to have the warhead much closer. Now, I think Professor Nacht has tried, and I think it probably does not take much effort to really put fear in your souls about how horrific these weapons are. These are the circles where, if for each weapon, a Hiroshima-type weapon or a modern thermonuclear weapon, so the altitudes would be different, but in each case of the circle, the altitude was picked to maximize the radius, the surface radius, where you would get an overpressure of 15 psi. That is Manhattan. In fact, you can see no borough of New York is untouched. And based on the fact that you basically have 100% fatalities within a radius, you can see what a horrific thing that is. The Tsar Bomba would actually make a circle that would go into Connecticut. Okay. Ditto, where you start, just due to the heat from the fireball, where you get massive fires. Whatever is remaining now will be basically swept up in a firestorm. Okay, let's talk about biological effects. Since I slipped about a lecture, I did not get a chance to talk about the different types of radiation and the effects on matter. And now, if that matter is biological matter, let me just state that slow charged particles, like an alpha particle or like a neutron, which is uncharged, but it normally will hit a proton. The proton will go lumbering off. Slowly moved heavy charged particles are very effective at ripping up molecules, sort of breaking bonds, and now taking stable molecules and turning them into free radicals and things like that, which then are very damaging to your chromosomes. So if you know a little bit of biology, you've heard about a double strand break. Your body every day is repairing hundreds, thousands of times a day double strand breaks. It just happens all the time. Once in a while, it doesn't get repaired correctly, and that could be the beginning of a cancer. So if you have, now alpha particles are normally fine because not a problem because they'll stop in a layer of skin, but if you inhale radon or anything like this, or you ingest something such that as an alpha emitter, it now can actually hit, it will actually go crashing through several cells and ripping up, your genetic material and so forth. That is very, very damaging there. Beta particles and gamma rays, which will knock off electrons, which form beta particles, are lightly penetrating. They're highly penetrating, but leave very little what's called linear energy deposition. I'm an old-fashioned guy. I never really got into the new world of grays and sieverts. This is simply a rad, and now was called the gray, is simply the energy per kilogram. So that's just whether it's a stick of butter, a brick, or a human being. A rad is a rad, or a pumpkin, whatever. It's simply joules per kilogram that is absorbed by radiation. Now, when you talk about what was the biological effect, it depends critically on whether it is an X-ray, a gamma ray, or a beta particle, or an alpha or a neutron, and therefore you associate a quality factor because these things will all have a more or less deleterious effect on you as an organism, with things which produce slow-moving, charged particles, either a charged particle itself or a neutron which produces a charged particle slowly moving, being the most damaging to the organism. And this used to be called a REM, radiation equivalent man. I'm not a radiation biologist, and now it's called a sievert. This shows you at a height of 500 feet a simple 1 kiloton device, not much of a bomb at all. This is even a very primitive device. Even thousands of feet away, you are getting, you can get hundreds to thousands of rads absorbed, which is a very bad thing here. You saw in that chilling movie, the depiction from that movie, 1989 movie, Little Boy and Fat Man. And you were right, it was John Cusack, Michael, it was who was playing Louis Slotin in this criticality accident they had in Los Alamos in 1946. He did the calculation based on the distance away where people were standing from the table from where the pit went critical, and was calculating, even then they knew how to calculate this, where they were with respect to the magic number of 500 REM, which is LD 500, lethal dose, 50% of the time. Horrific death beyond here, particularly the body's worst fuse box is the body is actually programmed if these what are called the crypt villi cells, the stem cells in your gut, are actually programmed to undergo apoptosis, to self-destruct at 500 R, simply to prevent, we've evolved to prevent long-term cancer like that. But then you die a horrible death of internal infection and bleeding much higher levels, you are sick immediately and die just due to direct damage to your central nervous system. Even much less exposure immediately to that amount of radiation, and you will get nauseous and very, very bad things happen. Okay. Fallout, if in fact there is a surface burst that scoops up a lot of material from the ground into a cloud, and then like the Castle Bravo test, the Mike shot, and others that were done in the South Pacific, this cloud can go hundreds or thousands of miles carrying immense amounts of radiation, which then falls out or rains out. This gets personal. I was born in New London, Connecticut, grew up there, and there's Old Saybrook, and there's New Haven, and then our New Yorkers are down here. And you can see you've got the total integrated surface contact radiation there is very, very large, even at fatal levels if you're not inside. Good news is if you can get inside and wait and not very long, a lot of the fission products will beta decay, and then the danger is much less. Standard thing, what is the average human being? And this is what we have to teach people who are petrified of radiation needlessly. There's just normal background radiation just due to the fact that every part of the Earth's crust, concrete bricks that we make out of the Earth's crust, everything else, rock, stones we use in our buildings, is 1 part in a million thorium and uranium. You also have cosmic rays, which are pelting us all the time. That's just part of life. You also get a certain amount of radiation medically. Some people, actually, I've never had a CT scan, but if you have CT scan, you actually get a fair amount of radiation. But normally the calculus is that it's there to diagnose something that's more problematic that you need to deal with. And there we have it. And I'm done. A little bit behind time.
Well, we've thrown a lot at you.